Let's head back to the realm of correlations and covariance for a moment. What is the covariance between two random variables? Well, it's really just the L2 inner product between their centered versions. So if yn is a sequence of uncorrelated random variables, that just means that the expected value of yn centered times ym centered is 0 for n not equal to m. And that is just the L2 inner product of those two centered random variables. Where remember that y centered means y minus its expected value. In other words, a sequence of uncorrelated random variables is a sequence of random variables that, after centering, is an orthogonal sequence in L2. Now, when we have orthogonal sequences, we have Pythagoras' theorem, and we have the Weierstrass M-test for convergence. Putting those together, we have the following very elementary proposition. Suppose that yn is a sequence of uncorrelated random variables, and suppose that the sum of their variances is finite. Then, the sum of the centered versions of those variables converges in L2. Now that's just a statement of a standard completeness result for the Hilbert space L2, because the variance of a random variable yn, which is its covariance with itself, is the expected value of the square of the centered version, which is its inner product with itself, or the L2 norm squared of that centered random variable. And so this assumption here is just the assumption that the sum of the squares of the L2 norms of the centered random variables is finite. But under the assumption that it's an orthogonal sequence, Pythagoras' theorem says that the sum of the squares is the square of the sum. And if that's finite, then because L2 is complete, the sum converges in L2. To be a little more pedantic about that, let's just let Sn circle be the sum of yj circle, j going from 1 up to n. Then we can use the above observation to show that Sn circle is a Cauchy sequence in L2. If we look at the L2 norm of the difference between Sn and Sm centered, and square it for good measure, then that is just the L2 norm squared of the sum, j going from m plus 1 up to n, here assuming that m is the smaller of the two, n and m, of yj circle, L2 squared, and by Pythagoras' theorem, that is equal to the sum, j going from m plus 1 up to n, of the L2 norm of yj centered L2 squared, thanks to the orthogonality assumption. And therefore, by the assumption that the sum of squares of all of them is finite, as n and m both go to infinity, this sum of squares tends to 0. So that shows that Sn circle, which is the sum j going from 1 up to n of yj circle, which is yj minus the expected value of yj, is a Cauchy sequence. As we proved, L2 is complete, and therefore this is a convergence sequence, which is exactly the conclusion of the theorem. If we were only interested in L2 sums, this would be the end of the story for all of the tools we need to develop to fully prove the strong law of large numbers. But we're not just interested in L2, we're interested in the stronger notion of almost sure convergence. So here's the question. Under these conditions, does this sum converge almost surely? Well, the answer to that is almost surely not. In general, there's no reason to expect an L2 sum to converge almost surely, unless we upgrade the assumptions from orthogonality to superorthogonality, that is, independence. And that brings us to the main theorem of this lecture, Kolmogorov's Convergence Criterion, which exactly says that if we replace uncorrelated with independent in the assumptions, then the conclusion of L2 convergence can be upgraded to almost sure convergence in that last theorem. To be precise, if yn is an independent sequence of L2 random variables, and the sum of their variances is finite, then the sum of the centered random variables converges not only in L2, but almost surely. In particular, if we also assume that the sum of their expected values is finite, then the sum of the yns, centered or not, converges almost surely, and also in L2. Now that last statement simply follows from the fact that the sum of yn will then of course equal the sum of the centered yns plus the sum of their expected values. So we need to prove this strong, almost sure convergence result under the assumption of independence of these L2 random variables. In order to do that, we're going to prove our first example of a maximal inequality. Take our sequence of independent random variables, and let's assume that their expected values are already 0, so that I don't have to keep writing those silly circles on top to center them. Now set Sn to be the sum of the first n as usual, and let's go ahead and assume they're in L2, which will be fine for this lecture. We could estimate the size of this Sn using Markov's inequality in the L2 setting. And that tells us that the probability that the absolute value of the sum is bigger than any parameter epsilon can be bounded above by 1 over epsilon squared times the expected value of the square of the sum. And in this case, since the yns are independent and therefore uncorrelated, we can use the Pythagorean theorem once again to write this expectation as the sum of the expected values of the yj squareds. Great. But what can we say about this quantity, the maximum of the sums from 1 up to n? That is, the maximum of absolute value of S1, which is just y1, absolute value of S2, absolute value of S3, up through absolute value of Sn. Now note, if the y's were non-negative random variables, then adding each new yn would only increase the sum, and so the maximum would just be Sn, and we'd be back in this situation here. But we've assumed that these have mean 0, and so they are almost certainly not non-negative random variables. So this maximum is different than any one of the Sj random variables. It turns out that getting nice estimates for this maximum is often a good way to prove almost sure results instead of L1 or L2 results. Now this maximum is certainly bigger than or equal to this guy here, but that inequality goes in the wrong direction. We can't just conclude that the probability that this one is bigger than or equal to epsilon is smaller than this, which bounds a smaller thing being greater than or equal to epsilon. But it turns out that we can draw that conclusion, not from Markov, but from Kolmogorov. So here is Kolmogorov's maximal inequality. With yn and Sn as above, the probability that the maximum Sn star of the absolute values of the sums from 1 up to n is bounded above by 1 over epsilon squared times the same thing, the expected value of Sn squared. In fact, it's bounded by something that's potentially even smaller. We can add in here the indicator that Sn star is bigger than or equal to epsilon. We won't really have much use for it in that form, although it is potentially a better estimate than the one without it. However, notice that this, being a function that is less than or equal to 1 and non-negative, allows us to simply do the blunt estimate and get the same result that we had from Markov for Sn in absolute value. And again, by Pythagoras' theorem, this is equal to 1 over epsilon squared times the sum of the L2 norms squared of the yj's. We're going to prove this maximal inequality now, and then we will use it to prove Kolmogorov's convergence criterion. The proof that we're going to give here is your first encounter, or maybe pre-encounter, with a fundamental idea that sets probability theory apart from analysis. This proof, although we're not going to use that terminology, involves stopping times. And right here and right now, you're going to learn whether you're really a probabilist at heart. Here's the idea. Fix a tolerance epsilon, and we'll let tau be an integer. It's the smallest integer for which the absolute value of the sum indexed by that integer exceeds epsilon in absolute value. So tau is a random integer, to be clear. Also, it might not be an integer because it's possible that Sj just doesn't exceed epsilon, and so there is no smallest such j. In that case, we would say that tau is equal to infinity because we declare that the infimum of the empty set is infinity. So this is a random variable tau that takes values in the integers together with plus infinity. Now, we'd like to understand the sigma field generated by this random variable. It turns out that it's closely related to the ones from which it is constructed, because we can characterize this event, that tau takes the value j for any particular integer, in the following terms. What does it mean that tau equals j? Well, tau is supposed to be the smallest time, j, at which the absolute value of Sj exceeds epsilon, which means that for all smaller times I, absolute value of Si must be less than epsilon, but Sj in absolute value must be bigger than or equal to epsilon. That is to say, this event is exactly the event that the absolute value of S1 is less than epsilon, the absolute value of S2 is less than epsilon, and so on through the absolute value of Sj minus 1 less than epsilon, and absolute value of Sj is bigger than or equal to epsilon. Now remember what these random variables are. S1 is just y1. S2 is just y1 plus y2, up to Sj minus 1 is y1 plus yj minus 1, and so on. And so it is clear that this event here, the event that tau is equal to j, is in the sigma field generated by y1 through yj for each j. It is explicitly written here as the preimage on a Borel set, a product of a bunch of intervals and the complement of an interval, under functions involving the random variables y1 through yj. That's going to be important shortly. Now, let's look at the event that we're interested in, the event that the maximum Sn star is bigger than or equal to epsilon. Well, the maximum being greater than or equal to epsilon means that there exists some j between 1 and n for which absolute value of Sj is bigger than or equal to epsilon. But that is exactly to say that the infimal time at which that occurs is less than or equal to n. So, the event that the maximum Sn star is bigger than or equal to epsilon is equal to the event that the time tau is less than or equal to n. Great. Why am I showing you all of this? Because it's going to allow us to prove our estimate in a very quick and clever way. Let me just introduce some notation here so I can stop writing all of these indicator functions. If x is a random variable and a is an event, then we write the expected value of x colon a to mean the expected value of x times the indicator function of a. Just a word of warning, this is not the same as having a vertical line there which denotes conditional expectation. That's something we'll get into a little bit later. We are going to pronounce this as the expected value of x given the event a. So what we can say now is that the expected value of Sn squared, given that the maximum of Sn is greater than or equal to epsilon, is the same as the expectation of Sn squared, given that the time tau is less than or equal to n. Now, that event, indicator that tau is less than or equal to n, of course can be written as a sum, j going from 1 up to n, of the indicator that tau is equal to j. In other words, the event that tau is less than or equal to n is the same as the disjoint union of the events that tau is equal to 1, tau is equal to 2, up to tau equal to n. And so factoring that expected value over that sum of disjoint indicator functions gives us that this is equal to the sum of the expected value of Sn squared given that tau is equal to j. Now we're going to use a trick which will become our bread and butter later on when we get to the study of martingales. Let's look at this Sn squared inside that expected value, and let's write it breaking up in terms of Sj inside this sum. That is, Sn can be written as Sj plus Sn minus Sj. Why would we do that? Well, just foiling it out, then we can write this as Sj squared plus Sn minus Sj squared plus 2 times Sj times n minus Sj. And keeping in mind what Sn is, notice that Sj is the sum of y1 through yj, whereas Sn minus Sj is the sum yj plus 1 through yn. That's relevant because of our assumption in this problem that the random variables y1 through yn are all independent. And so by the grouping lemma, this is independent from this. So these two are independent terms. Now we're taking an expectation of them, and we know that expected values of independent random variables factor. But we have to be careful because we're also multiplying by an indicator function here, but that indicator function is measurable with respect to those random variables. And so we should put this indicator function together with that term there, which will allow us to factor this as follows. So the expected value of Sn squared, given that the maximum Sn star is bigger than or equal to epsilon, can be written as this sum of expected values. But in this cross term here, if we group the indicator that the time tau is equal to j with the random variable Sj, and notice, as we just said, that each of these is measurable with respect to the sigma field generated by y1 through yj, while this one is clearly measurable with respect to the sigma field generated by yj plus 1 through yn. And since those two sigma fields are independent, these two random variables are independent from each other, which means that their expected value of their product factors as the product of the expected values. But Sn minus Sj is just the sum yj plus 1 through yn, and each of those terms by assumption is centered, which means that the expected value of their sum is 0. So that tells us that this cross term here is not present in the sum. And so this expected value is actually just the sum of the first two terms, which are each squares. So this expected value here is of course non-negative, which means that we can just toss it out if we're looking for a lower bound on this quantity, which is what the maximal inequality is. And so this is greater than or equal to this sum here. Now what can we do with that? Well, we'll sort of translate it back. This is the expected value of Sj squared times the indicator of the set where the time tau is equal to j. But again, that tau is equal to j is the event that S1 is less than epsilon, S2 is less than epsilon, Sj minus 1 is less than epsilon, and Sj, an absolute value, is greater than or equal to epsilon. So that is contained in the event that the absolute value of Sj is greater than or equal to epsilon, which means that Sj squared times the indicator that tau equals j is greater than or equal to epsilon squared times that indicator. Because on the set where that indicator is non-zero, Sj squared is greater than or equal to epsilon squared. And so we can bound from below as such, but pulling the epsilon squared outside, that's just epsilon squared times the sum of the probability that tau is equal to j running from 1 up to n, which is the same thing as the probability that tau is less than or equal to n, which, as we established at the beginning of this proof, is the probability that the maximum Sn star is greater than or equal to epsilon. And that inequality is Kolmogorov's maximal inequality. Wasn't that fun? All right, now we're going to see how to use a maximal inequality to upgrade L2 convergence to almost sure convergence. So here is the theorem we're going to prove. Once more, Kolmogorov's convergence criterion. If yn is a sequence of independent L2 random variables with the sum of their variances being finite, then the sum of the centered versions of the random variables converges almost surely. Let's prove this. Again, we're going to show that this converges almost surely by showing that it is almost surely Cauchy. So let Sn be the partial sum up to n. And let's look at the difference between Sn and Sm, assuming that n is the larger of the two. That's, of course, the sum of the terms from m plus 1 up to n. Now let's apply Kolmogorov's maximal inequality to that sum. That is, we're starting the index at m plus 1 instead of 1, as we did in the previous slides. So that tells us that Sn star, which this time means the maximum of the absolute value starting at m, which is exactly what we have written here, the probability that that is bigger than, and now let's be clever and make it epsilon 2 instead of epsilon, is less than or equal to 1 over epsilon over 2 squared times the expected value of the square of the variable, Sn minus Sm. And again, using orthogonality, which follows from the independence assumption, this factors out using Pythagoras as this sum here, which is the same thing as the sum, j going from m plus 1 up to n, of the variance of yj by definition of variance. Now, that's true for any fixed n, but now we can take n off to infinity on both sides. If we take n to infinity here, then this becomes the supremum of Sj minus Sm for j bigger than or equal to m. And on the right side, this becomes the sum of the variances from m plus 1 up to infinity. Now, our assumption is that the sum of all the variances is finite, which means that as m goes to infinity, that goes to 0. Now, that's almost like saying that Sn minus Sm is a Cauchy sequence, but to make it precisely fit, let's just look at this. We want the supremum over all j and k bigger than or equal to m. Then if we take m off to infinity, that's taking j and k both off to infinity, which is what we need for a Cauchy sequence. We'll do the usual trick and add and subtract the base reference Sm in between, bound that using the triangle inequality, and then each of those terms looks like this. And so that is, this supremum is less than or equal to twice the supremum over j relative to m. Therefore, from what we proved here, we see that the event that the supremum of j and k both bigger than or equal to m of Sj minus Sk being bigger than our reference tolerance epsilon is contained in the event that twice the supremum j bigger than or equal to m of Sj minus Sm is bigger than or equal to epsilon. But that's exactly what we bounded here in probability. So taking probabilities of both of these, we get that the probability of this event is less than or equal to the probability of this event, which goes to 0 as m goes to infinity. So at first glance, you might think that we've shown that something converges to 0 in probability, and we were aiming for something much stronger. But let's look more closely. What we've shown is that for any epsilon, the probability that the supremum over all j and k bigger than m of the absolute value of Sj minus Sk being bigger than epsilon tends to 0 as that reference parameter m goes to infinity. So indeed, that shows that this random variable, delta m, which is this m-dependent supremum, tends to 0 in probability. But that random variable, delta m, as a function of an integer m, is a decreasing random sequence. Indeed, if I take the supremum over a set that starts at m plus 1 instead of m, that's a smaller set of indices, and so the supremum can only shrink. So I have a decreasing sequence of non-negative random variables and a decreasing sequence of non-negative numbers has a limit. So therefore that limit exists in the non-negative reals. But we know that this sequence converges in probability to 0. If it converges in probability to 0 and it converges surely to some delta, it must be that that delta is equal to 0. And so we do get that the supremum over j and k bigger than or equal to m of sj minus sk converges to 0 almost surely as m goes to infinity. Well, that is exactly to say that sj minus sk goes to 0 almost surely as long as j and k both go off to infinity, i.e. the sequence sj is almost surely Cauchy, and by the completeness of the real line, it follows that that sequence, which is the sequence of partial sums, k going from 1 up to j, of centered yk, is almost surely convergent, which is exactly the conclusion of Kolmogorov's convergence criterion. There we have proved our main technical tool, which we will shortly use to prove the strong law of large numbers. But before we move off there, let's prove one cute result directly using the Kolmogorov convergence criterion. Remember that the sum of 1 over n is a divergent series. Similarly, minus the sum of 1 over n diverges to minus infinity. But if I put some 1's and minus 1's together inside, for example, alternating, then we get a convergent series that converges to plus or minus the logarithm of 2, depending where we started that series. So what if we put some pluses and minuses in front of those 1 over n's randomly? That is, suppose I take xn to be a sequence of IID Rademacher random variables. Rademacher are just Bernoullis on plus and minus 1 instead of 0 and 1. That is, x equals plus or minus 1 with probability 1/2 each. If these are independent from each other, then I'm just putting an independent random sign in front of each of the 1 over n's. And the question is, does that series converge or not? Does this behave more like the case where we have all 1's or minus 1's, or more like the case where we have alternating plus and minus 1's? Well, your intuition probably tells you the second one, and that turns out to be correct. If I let yn equal xn over n, these are independent. They're of course L2 because they're bounded random variables, and they're already centered because the Rademacher random variables are centered. Now if I just calculate the variance of yn, that's the expected value of the centered yn squared, which is the expected value of yn squared, which is 1 over n squared times the expected value of xn squared. But xn takes values plus and minus 1, which means xn squared takes value 1. It is just the constant equal to 1. So the variance here is always equal to 1 over n squared. Therefore, the sum of all the variances is the sum of 1 over n squared, which is finite. And therefore, by Kolmogorov's convergence criterion, the sum of yn centered, which is the same as the sum of xn over n, converges almost surely. There's no end to amusing other random series that we could analyze using this criterion. But let's now move towards using it to complete the proof of the strong law of large numbers.